All right, guys. Let me put up a warm up, and then now, admittedly, I think this warm up is very hard to solve. I don't know if you guys will get this. Okay, but I want to at least give this to you to try, and then that way it warms up your brain, and then we could segue into solving for this. So this is a continuation from last week. I put up 2 videos on use substitution already for just 5-minute videos on some tougher problems. Here's one of the problems I did not get to tape. Okay. So I want you to solve for the general integral function for this problem here. You may use u substitution. I believe this is the one. Actually, this one is a little bit more difficult. Let me try something that's a little bit easier. Still tough, though. Still deceptively very tough, okay? So again, don't get too frustrated if you cannot solve for this. Okay? This is a very, very tough problem. All right, so go ahead, work on the whiteboard space, and then have at it. Right? I want you to find the integral for cosine cubed x, or cosine x cubed. Yes, you can erase all that, yeah. Again, I do admit that this is a problem that, without given context in the beginning, this is very hard to solve on its own. This does require experience to see problems like this. This is not easy. Okay. In fact, if you solve for this, I'll throw in some extra credit, but just if you can, just to keep you motivated. It's not an easy problem. I think it's deceptively tricky. So, Allie, the du would be, I think, negative sine. So don't forget about the power rule. Remember, the 3 comes down. And then, 2, yeah.
Okay. I did something wrong there. Yes, see, I have the same idea as Ben. Thank you. Good. Okay, so
How are you going to substitute that in?
Oh, okay, so that's and what would you do?
The question is, though, du is supposed to replace.
Oh, I see. So you divided both sides by
1 negative sine x. So you take the integral, then you have. I see. Okay, so go ahead and try that, and then try to find the derivative solve so we can see
of this.
no. So
I get an integral.
you have this, and then don't forget you have times 1 over negative sine x. Right?
Yeah, there should be that.
Oh, so don't think. So I'm just saying that you have this here. And then at this point, plug back in u.
Oh, right.
And then take the derivative of this and see if it.
So
I am so wrong. I didn't even think that was you. I mean, you.
I think you can make it.
Yeah, you can.
Oh, I thought it was easier to make like the thing that was inside.
Is it?
Whatever you would decide to do. I mean, I don't know. I'm just saying to solve it at this type of problem,
require the x-rays and the technique.
Okay. That will gain in the month?
Huh?
That will gain in the month?
You'll be in a month, yes.
Oh, okay, good.
Now take the derivative of this and see if it goes back to cosine QT. It will require a lot of work, though. Derivative of 1 over cosine.
Hey Christina, we're solving this ridiculous problem here that looks deceptively easy.
I know we have to use an identity. I'm trying to figure it out.
You do have to use an identity, but it's in such a way that
I was thinking of the 1 minus sine x squared or sine squared.
yeah.
Is that the right one?
Yeah, you will have to end up using it. Yes, that's correct. Just in which way, you know. All right, guys, I'll give you guys like another minute, and then I gotta stop you. This is just intensely hard. I think Ben and Aaron are on a good path to try some trig identities. Okay, don't worry, Ali, Deja. I would have been right where you were. Okay, that was definitely me in high school. Did not know what was going on. These types of problems were ridiculous.
He looks like one of those scientists.
Yeah, he does. Yeah. And he looks like one of those quick scientists because he's like because he's like 2 foot shorter than everybody else right now for the time being, you know. You guys ever heard of Doogie Howser? No? You have? Oh, that's like that's like a really old TV show where they had like a smart little genius doctor. So he's
Yeah.
okay. All right, Ben. I hate to stop your roll here. Did you get your answer?
Yes. It's that.
Okay. All right. So you have
Is he
that.
right?
He is slightly incorrect,
Oh.
but he was correct.
Simplified.
So let me see if I can kind of break this down a little bit simpler. Now, trust me on this. This is not something. This is not something that. This is not something I expected you guys to know. Okay. Now, what made this problem actually more difficult than it initially looked? What part of this problem made this more difficult than we expected? Huh? Yeah, cosine cubed. It's the fact that it's cubed, right? So whenever you see a trig function that is cubed and they take the integral, like a problem like this, what you're supposed to do, okay, you're probably not going to like this at all. It's very uncomfortable to see something like this. You want to split it off into something that has cosine squared x times cosine of x. Well, to a certain degree, yeah, it's like, I guess that makes sense. That would have been my response, okay?
So,
Yeah.
what I plan on doing was substituting the cosine squared with 1 minus sine squared x. Would that have been the correct step to do?
That's exactly it. The reason why we want to separate this into cosine squared x and cosine x, it's not so much for this piece. This piece will come into play in just a little bit when you're taking the du.
Oh.
What you want to do, so I think Aaron can kind of see it right now. What you want to do is you want to separate it, at least in a way to where you have cosine squared x, and you can use a Pythagorean identity. Or I'm sorry, yeah, is it Pythagorean identity? Or you want to use a trig identity that you might know of already. What is cosine squared x also equivalent to? Yeah, it's 1 minus sine squared x. A little bit mean because it expects you to know that and remember that, okay? So if we think about that, this will now be replaced with 1 minus sine squared of x, okay, times cosine of x. So this is now replaced with this. Why is this significant? It helps in our u substitution. That's only half the battle, I would say. The other half would be to figure out what the u is. Now, just imagine yourself sitting at the board trying a whole bunch of different u's. I will save you some time and skip to the step where we figure out what the u appropriately is. It's actually
1 minus sine squared x, right?
It's actually just just sine of x. Again, not intuitive, not in the way that we figured out u substitution problems previously, okay? Again, this is just a type of problem, a very specific, special type of problem that you might encounter in the future. So I would still kind of get this in your repertoire, or like your variety or your skill base here. Get down these types of problems where it's a cube of a trig function, okay? These are the steps that you're going to have to take to figure these out, right?
For every trig function.
Just in case that you're ever met with a cubic trig function, which I do believe is a possibility on the AP exam. Some in the book I can look at and be like, I don't think you're going to encounter that in an AP exam, truthfully. Some, however, though, you might actually see, and this is one of them, okay? So if u was cosine of x, what is du? Yeah, cosine of x.
I got a much simpler explanation. That's ridiculous.
Still amazing that he was creative enough to come up with something like that. I can barely follow what's going on. Okay, so now the next step is once you establish your u and your du, you're going to substitute it back in wherever you see sine of x and wherever you see cosine of x. I see sine of x squared, so what is that going to look like? It's going to be 1 minus what now?
U squared.
U, but not just u, but u squared. Since u is only sine of x, and this is sine of squared x, or this is sine squared x, this has to be u squared, times du. Oh, and I'm sorry. This is du is equal to cosine x. Technically, it's cosine x dx with respect to x. Remember, whenever you take like a derivative, you have to say like that dx. The reason why that's nice is that du replaces all of this, including that dx sign there, okay?
Can you zoom out?
Yeah, sure.
This was longer than I thought, so I'm going to run that first.
As you notice, my writing's getting bigger and bigger. I guess it's like subconsciously I'm like getting more excited about the end. Like, yeah, it's getting crazy now. Okay, I'm going to continue.
So I can see all of it.
Sure, okay.
Thank you.
Let me see if I can zoom out even more so I can continue the problem. Okay. So the next step now would be to take the integral of this. Just take the integral of 1 minus u squared with respect to u, okay? Right, so what is the integral of 1 minus u? The antiderivative of 1, let's say. If you had to go, not take the derivative, but go backwards. What would be the antiderivative for 1? You would say x, but remember, we're talking about in terms of which variable. Is this? So instead of x, you would say u. Minus, and what is the antiderivative of u squared? Not x squared, but u squared. I'll help you out. It's 1/3 u cubed. And then all you have to do now is plug back in u. Sine of x minus 1/3 sine, whoops, I think I kind of put too many parentheses, cubed. And there we are. That's it.
What happened to the first cosine?
The first cosine?
Like the du.
Once we did the u substitution here and it accounted for this.
No, I mean in the beginning you had like cosine squared times cosine.
Oh, just remember that's, if you work this out and you take the derivative of this, you will end up something like this or right here. If you take the derivative of this right here, you're going to end up with cosine cubed x. That's what happened to it. Because you took that antiderivative, that all goes away, and you're only left with this. Okay? So, yeah. So just take my word for it, and then practice it, and then try taking the derivative of this and see what you end up getting. So that was not an easy problem in the slightest, okay? Okay, so that's going to be, I think I had one more tough U substitution problem, but it really only helps in the context of the homework, and not necessarily the big AP exam. So I might try, I still have to make a video for that one, but this was the one I really want to touch base with you guys on, okay? All right, so we're gonna move on now. We're gonna try to hit 7.3 and 7.4 into what I call separation of variables. Not me personally, but we're gonna go over separation of variables.
7.3 is 7.4?
Yeah.
But on the cover sheet it says to skip
I need a review.
Oh, I'm sorry, it should just 7.4 then.
Okay.
So I just keep thinking separation of variables is its own section.
That's integration by parts.
Integration by parts, I mean, yes. Yeah, there's no 7.3, that's correct. Okay, so we're going to go over 7.4, exponential growth and decay. So I do apologize, it will be a little bit more direct instruction than usual for this segment here. Okay, we're going to go over exponential growth and decay. And basically what you're going to see is exponential problems, right? Problems with exponents, and then it's going to represent either you're growing in terms of something, money, time, or whatever it is, or you're losing a lot of stock or money or whatever the case may be, okay? Before we do that, we have to learn about this skill. It's called solving by separation of variables or integration by parts. You might know it as integration by parts. So this is a kind of a subtopic here within this section. And I'm going to give you one right now, or I'm going to go over a sample problem that you may see in your homework, and then I'm going to give you one that's a little bit simpler to try, okay? So what if I asked you to take the integral of this? With what we know traditionally to do with integration right now. What if I asked you to take the integral or the antiderivative for this? What is a glaring issue with this problem? Huh? What do you say, Allie?
There's X and Y.
Yeah, there's X
There's
and Y.
like two, I forget.
Yeah, they're variables. That's absolutely correct. We have two variables going on here on the same side. So yikes, that's not good. I don't know what to do now. Well, traditionally algebra, what would you do if you had a y and an x on one side? Or both sides of the equation?
Solve for y.
How would you solve for y? What would be
Manipulate the equation, get y on one side.
y on one side? That's the same thing here, okay? Now we're just doing it at a higher level, right? So really, at a higher level, it just means multiplying and dividing. Y isn't. Okay? I mean, well, and then you add in some antiderivatives, but still, that's all really amounts to. So let's treat it as that, okay? You're going to divide both sides. Let's try to get all the y's on the left side, just kind of like I think that's intuitive for us. We might have learned that way, to get all y's on maybe the left side and all the x's on the right side. It's completely arbitrary, okay? So we're going to divide one side by y plus 5. And whatever you do to one side of the equality sign, you must do to the other, which is you can either divide this whole fraction by y over 5, or you can look at it as multiplying it by 1 over y plus 5. Okay. What you should be left over is dy over y plus 5. Technically, will be multiplied to dx is equal to x plus 5. This does still not look very pretty. How do we get all the x's to the other side now?
Times by dx.
That's all we got to do. As intuitive as that sounds. So now we're left with dy over y plus 5 is equal to x plus 5 times dx. Still pretty tough. Oh, and for some people, for this next step, it helps them to see it like this. 1 over y plus 5 times dy, just to rewrite it, okay? You'll kind of see why I chose to do this, okay? They chose to separate the dy from the y in the same sense that you always see whatever x plus or x squared or whatever the x statement is being multiplied to dx, right? You're traditionally used to seeing this. You're just not used to seeing a dy, okay?
Substitution.
Well, there's no point substitution yet until we take the integral.
Did you
Yes.
like take an integral of both sides?
So that's what I was going to say. We still need, I want to find the original function, right? You see how we're still in the derivative state? We want to take the integral, right? But now what you might not be familiar with is if you take the integral of one side, you still have to take the integral of the other side. And you can do that. We've been taught that we can do that. We've done that in the past. Like if you remember implicit differentiation, where we took the derivative of a y and a whole bunch of other variables, it's the same thing. Yeah.
Okay, so when I do it, instead of doing 1 over 1 plus 5, I do parentheses 1 plus 5 negative 1.
You can do that too.
But when you do the integral, you're adding 1 to the exponent, so the exponent is 0.
Well, that's why we don't use the power rule. Do you remember what the integral would that be? Or of something that is to the negative first power?
Natural.
Say that again?
It's natural.
So give me 1 second. I love that you brought that up. I always forget this too myself, okay? So you take the integral of this. Let's first, well, this will require use substitution, but let's take care of this one, as Allie was saying, right? Allie was saying this. Hold on, Mr. Wee. This is still how I see things. I see it as this, right? You're like, how the heck do you do that? Because if you take the power rule and you add 1 for the exponent, then you should get 0. And then we'll continue off from here, right? Well, the integral for anything to the negative first power is just this.
Oh, is that?
Mhm.
Is that a rule?
That is a rule. That is a older rule. It's okay. I myself always forget this rule, and I'm teaching calculus. Okay, I mean that may not sound good, but yes, I still always forget this one. Okay, yes, Nathan.
So the only one is to the negative first power.
What's that?
It's only to the negative first power or the all negative?
It's only to the negative first power. Only to the negative first
Only
power.
negative first?
Yeah, everything else you can use the exponent rule, the standard power rule.
So if it was -3, you go -3 plus 1 over
Mhm.
-2.
It's just this particular situation. Okay. Yes, Nathan.
And then, so when you add the absolute value brackets,
Oh, that's right. The absolute brackets right here. Sorry, it is technically absolute value.
so is it always use that rule?
Yes. So over here, if this confuses you, you may use substitution to make sense of this, but what you will end up getting is x plus 5 to the second power 1/2. Is anybody confused by what I just did? Yes. Okay. Okay, so if I do it to the side, let's say that I did u substitution for just this situation. I would set my u to be x plus 5, okay? And then my du would be, what would be my du?
One.
Just 1. With respect to x dx, okay? Whenever you take the derivative, you always got to add that d of x or d of whatever variable you're taking the derivative of. Give me 1 second. So once you substitute that back in, you're looking at u du, and what is the derivative of just u? Or not the derivative, the antiderivative. It would be u squared to the 1/2. The reason why I know that is if I go back to take the derivative of this, it'd be 2 carried down here, exponent would be 1, and then this is where we would end up. Okay? Yes.
So when
Sorry, Aaron.
So when you do it that way, you see that u equals x plus 5. Because when I did it without doing the u thing, I just did the antiderivatives of the separate, like x plus 5. So, like, I didn't do it as a whole.
Okay.
X plus 5, I did the antiderivative of x, and x is antiderivative of 5.
You still,
can't do that, right?
yeah, you can't necessarily. Let's see.
Why not?
Ooh, yeah, I see. That's the question that you're
Because
gonna ask
then
me.
I
Huh?
got x squared over 2.
No. Oh my gosh, Allie. You're absolutely correct.
Is that correct?
Deja,
Wait, what?
you wasted space taking my notes. Sorry for having too much faith in me. Okay? As your teacher.
All I heard was, Deja, you're a waste of space.
No, Nathan.
That's right.
That's why I gotta choose my words more carefully. I would hate for you to relay that to other students. You know what he said to Deja?
You're not worthy.
No. And I don't blame you, Nathan. Out of 10 kids, there's always one student. It's like, what did he just say? Like, back up a second.
Yeah, that happened in environmental science last week, and Miss Michelle was like, I'm from the hood. If I said that, you would have known.
What? Wow. That is funny. That is humor.
Did Miss Michelle say that? I don't think she was like, that's not how I would have said it. I said something like that.
Oh, really? That's funny. So you're right, you guys. I'm sorry. You're absolutely right. No, you're absolutely correct. Okay.
Can you explain to me what you got?
I'm like pretty sure that yours would have worked too. Right?
Yeah, I think if you would have,
Oh, you don't need to. Just pointless stuff.
it is pointless. That is correct. I think, yeah, that's correct. Aaron, I think brought up a good point. I think my way still would have worked, but it would have been a lot more work because you basically have this x plus 5 squared times 1/2, and you would have to expand it like this.
Yeah. Oh, so it's the same thing.
It is. It's just, do you see that? How much troublesome? How much trouble that would end up instead of just doing individual integrals for x and 5.
Yeah,
Since,
that shows how that's the answer.
that's true. It is very true. I don't know. You can keep my notes, but I'm just saying I don't want to confuse you and be like, is that what I'm gonna have to do for no one? Like,
And it also kind of shows that this idea of view substitution is
still is consistent. Yeah,
You know, it's not just
limited to a certain context. It can be used almost in any context, even context where it's not needed. But yes.
which is kind of a cool thought.
By the way, are we finished yet?
Kind of like change. Oh, view substitution is kind of like the integral version of change.
Yes. That's absolutely what it is. That's the whole point. It takes into account the chain rule without confusing you with too many terms on the paper. That's all it really is. Yeah. All right. Are we finished yet, guys? Have you found out why?
No.
You're gonna love this part. Okay. Okay. So we have to do the E thing. Okay. We have to take E as a base, and then to get rid of the ln, the natural log. You can kind of see the exponent base E to the natural log of y plus 5. It'll sort of cancel out, and it'll leave you with y plus 5. The part that you're going to love, or possibly not, is this. You're left with this big, beautiful monstrosity.
Mr. Reed?
Yeah.
Why is the right side plus C
Yeah,
but the left side isn't plus C?
Because we only need one.
That is true. Yes. That's absolutely true because when you have a constant on both sides, yeah, that's just I did not explain that. That's actually really good, Allie. There is technically C on both sides, but once you move a C to the right side, in the end, it's still some constant we don't know. So it's only necessary to solve for a singular C value. Does that make sense? You might get something like this, okay? Like if it makes, you don't have to write this in, but let's just pretend down here we didn't have plus C. I'm going to write back in C, okay? We have a constant B and a constant up here, T, right? And I moved over T and B together, right? The whole point I'm trying to make is that it's still, regardless, you're still going to have one constant on a side that has both the constants, right? You have two constants, right, on both sides. You move it to one side, it doesn't matter.
So it's kind of like we've already moved it or something?
It's like we've already moved it. I skipped a bunch of steps to say that, basically, but
I just think it's weird because if you moved it, would they cancel out? Well,
we don't know if the constants would or would not.
If they do cancel out or not. Then
Yes.
it would just be 0.
C would just be 0. But we haven't solved that situation where if C is 0 or not, right?
Okay.
The fact is a C exists, whether it's 0 or something else, right?
Okay.
Yeah.
Thank you.
I kind of forgot what we were actually trying to do.
We're trying to solve for Y.
Is that it, or once we get Y? Is that
Don't just say that's it, okay?
Or-
That's a loaded question, right? Solve for Y. I hate you, okay? It's so much harder than that, Mr. Wee, okay? Like, I understand the thing, okay? All right. We're not finished yet, guys. We're just starting, okay? Y plus 5. Now, that C throws everyone off for a loop, okay? This is where things get real nasty, okay? I'm going to call upon and trust me, the sample problem I'm not going to give you isn't anything nearly like this, okay? The whole point I wanted you to basically get down was separate the y's and the x's on both sides, take the integrals of both sides, and then solve for y, okay? It's just, I chose a problem that led us down this rabbit hole, and we must finish this throughout, okay? So now we have this. If you have multiple exponents next to e and they're being added together, a property that you can do is e to the 1/2 x times e to the 5x
Squared. 1/2 x squared.
x squared, times e to the c.
So you're timing them all?
Yeah, and I'm only doing it to do one thing. The only reason why I'm doing it is to isolate e to the c by itself. And the reason why it's gonna be beautiful because I think your book does this in a way where it doesn't explain it, and I wanted to go over this problem so you would kind of see where it comes from. At least get an opportunity to try to figure out what's going on in the book. It's not just your book, but what your book will say is that you're going to end up with this. Your book leaves it as e 1/2 x squared, e 5x. Then I have a giant c.
Ah, that's genius. Oh my God.
Why is that genius?
Because it's still a constant. It's e to the c. E is a constant, so the c is.
So regardless, e to the c. Okay, let's just say c was some number, right? E to that number would still be some number. So again, it's still a giant constant. Again, I think your book though doesn't have a lot of these steps. It just goes straight to saying c. So that's where it gets really confusing. I'm trying to make sense. So one of the things that I still couldn't get was like, yeah, Deja was right. What about the constant on this side? So we had to explain that out. I missed that too. Yeah, Nathan.
Well, the way like to explain it, I think it was like you don't know it, so you just tack it on at the end so you can figure out later, like whatever matches the end of the problem. So, but like earlier when it was derivative of a constant, a derivative of a constant is always going to be just 0.
Exactly.
So that's what you can see.
No, that's exactly right. It's just in this context though, the reason why this gets really nasty is because you're going to get this. Y plus 5 is equal to c in the front. Let's move c to the front now, times e. And then I know you're going to not like this, but they rewrote this back as e 1/2 x plus, or x squared plus 5x.
You could have just pulled it out.
I know, but I wanted you to at least see that. I didn't want you to, like, how come you only pulled out e to the c, but not the other ones, Mr. Wade? You see what I mean? I want to do it step by step, so that
If
way.
we're solving for y, should we do -5?
Yeah. Now, Deja, I'm glad you brought that up, or else if you didn't ask that question, someone else would have been in the room like, I'm lost, and I hate that you subtracted 5 at the end. So why, okay? Why are you doing these things? But you're absolutely correct. So thank you, Deja, for adding that. Now your final answer, C, this giant constant, e 1/2 x squared plus 5x minus 5. Isn't that beautiful? Yummy. What? I'm sorry. All right? I lost my mind right. Okay, there we go. There's your final answer. It's just so simple.
Not really.
Yeah, I was just totally kidding. This is really tough, guys. It's not. I don't want you to I would like you to think. I would like you to look at this and be like, I can kind of simplify this, and it can be simple, but don't feel bad if it's not, because I don't think it's very intuitive and simple. Okay. Are you guys ready to try one?
By ourselves?
Not to this degree. Okay, you're not gonna have to deal with exponents and constants where you have to change the constants. Okay. It's
But we're not done with the problem. I thought you said this was the problem, the example, and then first we have to learn this sub part. I thought this was all the sub part.
Oh no, the whole subparts
Remember
with
the beginning?
yeah. What I meant, I'm sorry. I just meant like a bunch of C's and these rules with the
That was the
logarithms.
sub part?
That was like the little thing that I think I had to take like a hard sharp turn to kind of go through, right? But essentially, this is where I want to end with. Okay, so for now, here's your warm up problem.
You wanted to-
Sorry.
Let's-
Follow up problem then maybe. Okay, here's a you try this kind of problem. dy over dx is equal to y over x. Okay? Why don't we just start with that? All right, so please find a space on the whiteboard. Okay, I'm always a big advocate of whiteboard work. Okay, the nature of it is you can erase it very easily, so failure is not really a failure. It's just trying.
Oh, is it a family place?
Hey, Anthony.
Yeah.
Don't worry about it.
They like the milkshake. There we go.
Can I erase this?
You may.
Which stuff?
Yeah. This monstrosity.
Is this the same type of problem? Is that what we're doing?
Yes, it is. Except without the E.
Wait, stop. Stop. Is this the problem I wanted you guys to do?
No, it's not.
No, this is not the type of problem I wanted. Wait, did you guys already start? You guys like this one? We don't know yet. All right, hold on. Let's solve for dy of dx. Hey, hold on. Wait. Stop it. We're not doing this one. You guys were figuring it out?
No, we can do it differently.
Reluctantly, I'm sorry. Yeah, here we are.
Can you go over that? Should I erase later? Do you have time? Mr. Lee?
Huh?
Do you have time to go over that one though?
This one? Yeah.
The other one
Which one?
that you're trying to get the y over x.
Oh, this is perfect.
Oh, no, I won't have time for that one. No. Because we get. There's a lot more to cover in this chapter.
What?
All I get the problem.
You did it. Ben, we're doing a different one.
Come on, bro.
Yeah, let me move it over to the left so you can kind of see, Asia.
Oh, I guess you're right.
Okay.
Alright. Why is it negative? What's the integral, right? Integral?
It just
Do I do
says
integral here?
Not yet, but you kind of separated the very.
I don't want to make it more.
Am I supposed to separate this variable?
I don't think I separated.
I
don't understand
what
what you
want.
want.
Yeah, that's the way, yeah.
No, so.
Oh,
no, just a bunch of.
Yeah.
Then you have this curve.
So,
I don't understand why it's like.
Right.
why?
Oh, don't pay attention. That's just my thing. Is
Is
that all it's like that?
Can't do that.
No, but I get what you're saying, because that way it'd be easy to just move y over side.
I'm just gonna
Why
square
don't you
both.
just do it?
Ooh, Ellie, nice.
Should I just square both of them like that?
That's good. Yeah, that's good.
Control differential.
Oh, wait, to square? No, you can leave it as that. Just take the integral both sides.
Okay.
See, you are too, because that was why.
Yeah, it's a lie.
Okay.
Yeah, you can just flip it.
There you are. Yeah.
Yeah, you're right.
Yeah.
Let's do that.
A third x. And the other one is
Negative.
negative.
So it would be a
Yeah, so if you take y,
Or, wait, no, it doesn't.
You still have to take that to do.
That's natural log. What was the rule? Natural log?
No, it's a square.
so
That one's just
correct.
I think the antiderivative of y is negative 2. But
Is that a negative before the negative?
No.
Why is the -2? Right.
That's a
I
dot.
understand everything except for how
And the antiderivative of that is just -1.
Oh, in the book, it's just to help you separate it out.
Oh, you
Yeah,
got
it's
it.
negative.
Yeah.
That makes sense.
Yes, that's
Why do you don't? That's
actually good. Very good job, guys.
It's just like,
This is why
I understand what Allie's doing, except
child.
for the first part. Like, I don't understand why she
Oh
has
my
to
God.
use
Oh, there should be a C. I forgot a C.
I just did this to help myself.
Oh, yeah, they
That's
must
right.
Where'd you get
Mr. B,
two
is
from?
this it?
Child.
So as in, you should get.
Take the derivative of that. You get this.
So when you have that, let's make this a little bit cleaner. You're absolutely
Yeah.
correct. Why don't we take the reciprocal?
Oh.
That's right.
-3 over.
Is that it?
That's one
And
side
then
equation.
this is 1 over c.
Yeah,
That's it. Still c.
Because I did half the problem.
Oh, sorry. Is there another marker or are we out of markers? Let me get some more.
You had so many markers last week.
There was no blue.
We use one. It's not very good, but.
Wait, so is this like a wrong thing to do?
No, I know what you're doing.
Are we done?
Yeah.
I just don't know.
Wait, how do you
Okay,
get
right here.
Why does
You can just look at.
You have to get like y all by
This
itself.
squared,
One over
like
y.
it's literally just x
You have to
squared.
get y, oh wait, so all you have to do is just do negative
I think
1
what
over
I
y.
she just wanted to see it
And
separate.
then, oh, I'm sorry.
She's like did this thing on the side. She's like, so that's something that's not taught. It's just something that helps her with how a person is doing. Here, this is what you have
Like, I
here.
understand that, I just don't understand how it would be equal.
So you just do negative 1 over y, and then you just kind of add
Something like that.
negative
You can
y,
be like, oh, let me see.
and then multiply by y.
Because that's just
and divide
distributing
by everything to get y on top.
Yeah, and then
There's nothing special to that, it was just.
Bro, you know you're
It-
going sideways.
regardless, it works for her. She's got
No, you're
a
not.
method that.
What
makes
you mean
sense.
the word?
It's like
Oh,
giving yourself the
Oh,
ways t y.
And you said it's hard for you.
I won't stress over it now.
You know what I mean? Like, and it's like someone sees us. Like, wait, what does that have to do with this? It's like, you know what? I'm just stuff for myself. Okay, so
Me?
you don't have to worry about that. She's kind of saying the same thing. Don't worry about this. This is something.
I just want to understand it, I don't really.
You want to understand?
Oh, Martin, looks
No.
so
You
good.
want to be on the context of calculus.
And then, yeah, that's basically,
That's
that's it, except you have to do the reciprocal now.
Why?
Since
Maybe
it's
a
like
criminal.
1
Well, not a criminal investigator. A personal.
Huh?
Okay.
Thank you.
All right, guys, let's go ahead and stop. I'm gonna stop you right there.
Yeah, you do have a fancy.
He's a fancy man.
I can't sign.
He's the
I
refined
can't
man.
sign things with a bad
So
underground.
Yeah.
here's the solution.
Signature's different from autograph. Yeah, it is. Yeah, it is. You can't have the same.
All right, guys. So that's the solution. It's actually right in your book. It's the very first example in your chapter. So if you need to take notes, just make a note to yourself that this is in your textbook. Okay? They left it as negative y to the negative first power, as you could do x to the third, but it's also this as well. So here are the steps that you're supposed to do. You should have gone that. Oh wow, actually they kind of did something similar to what Allie did. Wow, it's
Yeah,
funny.
it seems like they did it in the book, so that's what I thought.
No, you didn't have to. No. No. I mean, what you could do is just. Do you see
It
on?
just helps you separate them.
Yeah, you can do. Yeah, or you can just do. We found that dy. Whoever wrote in green, is that Christina's? Yeah, Christina just wrote it as dy over dx is equal to x squared y squared, and then she started doing some math to manipulate the y's on the side.
How they
Oh,
got that in
you
the
lied to me. I was
How they got-
right.
which one? This here? In the book?
F of y equals y squared.
Oh, they literally just took. So they have this part here. Do you see this part here?
Yeah.
And then it's like they moved the y squared to one side here. Or actually, no, they didn't. So I guess all they're just saying is this. dy is equal to y squared. And then this x component is equal to that x squared. That's all they're trying to say. You see what I'm saying?
I'm just gonna pretend I didn't see it. I don't wanna trip myself.
Okay, yeah. Don't worry. Don't worry. Yeah, that's usually how I kind of used to study about things. I'm just not going to look at it. I'll do it later. I'm getting 90% of the other stuff I need to get.
Yeah.
But whatever works for you. Okay. So very good job. Now we got to start moving on to some other problems here. So let's see. Should we do that? Won't have time to do that. Okay. All right, so here's some more notes. Now we're going to move on to the second subtopic. We still have 2 more to go through. I think I only have time to go through this one. Okay, so here's number 2. It's going to be the law of exponential change. So what does this mean? You're going to look at topics such as growth, decay, half-life. So these are very, very different problems, okay? So, portal, half-life. So at least we have one person that still remember. It's an old video game. It's an old video game. Well, relatively speaking, it's pretty old. I think part 2 came out in like 2004. It's 14 years ago. Yeah. It's been a long time. Okay, so the general equation you will want to know for any exponential growth or decay, even when we're talking about half-life, you still have to know this general equation. It's y is equal to a times e k t, or you might see it as y is equal to initial y, like an initial value, e k t. You might have seen something like this before in pre-calc, right? But let me give you some context, okay? This equation can give you how things are growing. Let's say, I think the best example is within a company. You start with a certain amount of money, and you want to see how it grows over time. Everybody get that? You start with a certain amount of money, and over time, you want to see how it grows, right? So here's what I mean by that. You start with a certain amount of money. Get it? The initial value for y. Okay, so your initial value. You don't have to write this part. Initial value. You want to see how it grows over time. Okay, exponentially. This part will make it exponential with the base e and the k. Okay, so this is the exponential growth. However, what can also happen besides growth? You can also exponentially decay, and that can seriously happen. In fact, that a lot of people would argue for most people in the market that happens more often than a growth. Okay, that's why there's only a few companies, quote unquote, that have exponential growth consistently. Right? Exponential gains. Okay, so that's the general formula. Before we do that, you might want to see where this comes from. So you might ask what the k is. If you want to talk about the k, it's still within exponential growth. I believe that is, what is that? An exponential, what is that? I forgot what that is. Exponential, what do we call that? They called it something specific. Oh, it's an exponential constant. It's just an exponential constant. K is an exponential constant. So it initially started out as this. Where did we find out with anything with exponents, or how do we know any of this stuff? Okay, so it all started with this, a simple rate of you're changing your product over the change in time. Okay, and they started out with this simple problem. They knew some constant times y. And then, upon further investigation, you know now that you can integrate this by a separation of variables, as you just learned, right? That's why you need to learn this first to kind of understand where all this comes from. So this is sort of the proof for why this exists. So that makes sense, okay? A change in y over time starts with some constant times y. And then what you're going to do is you're going to take dy, and we know you're going to divide both sides by y, so I'm going to skip a few steps here. And then you're going to have k dt. All right? And if I wanted to rewrite that, that'd be like taking dy, or 1 over y, is equal to k dt, and then we take the integral of both of these values here. And then you know that you get ln y, okay, absolute value. And then I know it's hard to see this, okay, but it is kt plus c. Now, you might ask me, Mr. Wei, why is it kt and all these letters here? Just remember, k is it's a type of constant. It's an exponential constant, but regardless, it's some constant. It's a number, right? So I probably would have made you a little bit more comfortable if I gave it a number. Like, don't do this, okay? Don't do this in your notes. But let's just say it's 3. Does that make it more comfortable that now you see it's 3t? The antiderivative of 3 would be 3t.
Like 3x.
Exactly. But it's not, okay? But it's not in this context where you, oh no.
Because we're signing it now.
So you can have the empty thing?
Panic has overwhelmed me.
Okay,
but I have-
What's white out?
Oh, you want?
Why would you want it?
You can have it, Nathan. It's a clean bag of trash. There's no sticky things
So
attached to it.
why is dt just dt? That's my question.
What'd you say?
Like derivative with respect to t, why is it just become t?
It's the same thing as this, Nathan.
But it cancels out though, usually, the whole thing.
It does. What is the antiderivative of 3 with respect to x?
3x.
And then it disappears. The dx
Maybe
disappears.
you're thinking about it as a derivative.
Yeah.
Derivatives it would cancel.
Maybe the
It's
cheese,
not derivative.
like,
No, it's an integral.
So when we take the integral, it's like this. If you had to make sense of it, it's like taking the antiderivative of derivative x. What would happen to those terms?
It cancels out.
Yeah, that's exactly what happened.
I think the
But,
cheese
but,
throwing
the,
them
but the
off.
whole thing
I'm actually.
is d of x. So like
Uh-huh.
this oh god. That would just become nothing, right?
Yeah.
So then why is there still an x left?
Because
Because there's a K.
So this is what I was just talking about. Hold on. So
What's the derivative
go
of
back.
3x?
Hold on.
Three.
So this is a constant, right? With respect to t.
Right.
What if I made it and I said it was a constant? Right? It's some kind of number. Let's just replace this with a constant number. Give me a number.
5.
Okay? And I take the integral of 5 dt. What is the integral of 5?
5x.
5x or 5t, right?
Oh.
But
oh.
I'm just saying in general, it's some constant. It's not really 5, it's just a constant. So that's what I'm trying to say, okay?
Got it.
Just wanting to make it a little bit more comfortable.
That
Throw
way
you off.
I figured it out. Because it's an integral, not actual.
We're not finished. We're not done
Wait,
there.
there's more.
But wait.
Just in case you thought you got it, now you won't.
Yeah, I'm just kidding. Okay, hold on. We have e to the ln of y is equal to e to kt plus c. This will sort of cancel out, and you'll have y is equal to e kt. Now, remember what I did here, ec. Remember that? So now it was kind of necessary for me to go through that problem earlier, because now you won't be confused if I do this next step and saying that there's a big giant c in place of e to the c, e k t.
And that's like the A, which is the initial value.
And just like the,
Yeah.
does
Sorry. Yeah.
Sorry, does y stay absolute value when you take each natural value of absolute value y?
It can be negative because there's an
No. Actually, this is what your book specifies. Let me go back. Yeah. Actually, they say c could be plus or minus to compensate for that. So since this is plus or minus, we'll kind of embed that property onto the right side, saying that's plus or minus. So yes. So Nathan, you're absolutely correct. Yeah. That absolute value transfers itself over here to this side, saying that if you're taking the absolute value y, this could be a plus or minus for that matter.
But I don't think you need a plus or minus because I mean technically C is always going to be plus or minus.
So again, another good point is that if it's plus or minus c, again, it's just probably just c, whatever c is. So it gets really tricky. Basically, this is where you need to end up, okay? And as Christina was saying, if you look back to the original equation, what is the only thing different from what we started with, what we started learning with, as opposed to what we have down here? The c.
A is a C.
And it's arbitrary. I just called it C. I could have called it anything else, right? That's the same thing up here that you see. Remember how I told you that initial A or Y0 is whatever money you started with? Whatever money you start with. Let's say I put in $50, right? I put in $50, and then over time, as long as I know what K and how much time I got, I want to see what that money looks like in the future, right? I plug it into this equation. So basically, this is the same thing as what we started with. A, it's the initial, oh, yeah, it's the initial value. They're all the same thing, okay? In this case, it's arbitrary. I can call these anything that I want, right? But I have to know what these things serve, each of these variables, what they serve as. I understand that these initial values serve as an initial value that you're putting in, okay? I understand that E serves as a base of 2, it represents 2.71, some kind of number, okay? K is a constant value. T is a time value, okay? As long as I understand what the purpose of each variable is, I can call them anything that I want. Okay, I can call a pen a pencil if I wanted, even though it may not make sense to you. In Mr. Wee's world, in my head, it makes sense to me. Okay, because it's arbitrary in my head what this means. Okay. Okay, I don't want to teach you how to become psychotic now. Okay? So let's stray away from that. I'm just saying it's arbitrary. Okay? What is Mr. Wee actually teaching you guys? I don't know. I feel different. Yeah. Okay.
No, it's always has a second meaning.
It always got a second meaning. Okay. All right. Now let's give you a context where you solve for C. What? Okay. So let me give you not a practice problem necessarily, but a critical thinking problem. Something that I did not go over with you, but might not be as hard as it sounds. What if I gave you K and I gave you this? Y of 0 is equal to 100. And I want you to write, you see how I gave, we knew that, actually, yeah. I want you to give me the actual equation for this context. The general equation is this, C, E, K, T, right? I want you to give me something more specific. I want you to give me a Y that actually has a value. I want you to give me the value for C. I want you to plug it. I want to have an actual value of K as well. So I want a C, an A K, and the T can remain T, okay? That's it. This is going to be your AP question for the... All right, never mind.
Is that all?
That's all you need to do.
Yeah. I got you.
Why are you gonna mention that?
Why did you say no, Aaron?
What? There wasn't a no. It's completely correct. I was just kind of surprised that was it.
Yeah, that was it. I don't know. Some people should really struggle with that. Like, I don't understand what's going on. They spend like 10 minutes over it. What was your question? Allie, what was your question?
Oh, I didn't have a question. I just think it's
Oh, you're just done. Okay.
If I can do yes, then you're like,
All right. All right. Then it's just gonna be more direct instruction till the end. Then. Okay. All right. So what if I had a K value? So don't write this down. What if I had a K value that is greater than 0? Critical question. Would I have a growth or a decay?
You would have.
How would you know that?
because your exponent's positive.
If your exponent is positive, what would that mean?
It's increasing.
So you're,
Be like, whoa. Y is going up as A is high.
if I had
A
a
increases.
K value is less than 0, so if I had a K value that is less than 0, then I have a decay. Okay. So my third subtopic is just something that they cover in your book. Is just reminding you that if you have a K that is, now you can write this part down, K is greater than 0, then you have growth. Okay. And then your decay simply is that K is less than 0. If you need to remind yourself what the context of what K is coming from, okay, just write down the equation for growth and decay. It's Y is equal to A E K T, and over here as well, just to give you a reminder. Remind yourself of the actual equation. I think I have time for the last subtopic, which is a half-life. You guys ready for the half-life?
I hate this one.
I hate you.
We have them in like
Do you? Yeah. I think-
It's not this complicated, but I already get the algebraic form.
No, it's just the decay of an element, right?
Yeah. Oh, do you understand what the concept is?
Yes. Oh, sorry.
No?
I didn't. I never asked you.
Well, over time, let's say that this is a piece of carbon. Over some amount of time, every element has its own half-life. That's just a time in which half of the substance disappears, or
So-
just
Carbon is insanely large.
carbon is insanely large. But let's just say that we had like a half-life of this over here.
A singular day.
What? I see. Whoa, that would decay quickly. Okay, all right. Let's.
Yeah, that's so simple.
So, how many particles of carbon do you guys see? Do you guys think is in here? You guys don't. You make it
A bajillion.
a bajillion.
500.
Huh? Let's just go with 500 carbon particles. Okay, that's
Like a rational.
these are big carbon particles, but 5 carbon particles. Okay. How much time do you think it would? So, this is just conceptual. Okay. Before we go on to giving you what the formula is. So, how much time do you think it will take for half of these particles to like just decay out naturally? Just to like, because you know things over time decay, right? Like you lead something in the sun, decays, right? It rots. How much time do you think it'll take for half of this to kind of decay?
50 years.
50 years, right? Well, we're pretty old, right? We're not. It's not going to be a day, but it could be. You know, you never know what we're talking about, right? 50 years. 50 years. Okay. How many particles do we have?
250.
Oh.
Because half it's gone, right?
I thought you meant total.
Okay. And then, what do you think is going to happen in another 50 years?
It's all gonna be gone.
No, 125.
No.
Oh, another half.
Half of. Yeah. So let's say that I don't know, like we're looking only at the top half now. It's not literally like that. It's like this, but like half it's actually
There's
gone.
space inside that.
Okay, but this is half of it's gone now, right? Another 50 years, half of that is gone. Okay, but half of that.
Right.
125.
Well, it wouldn't be perfect because, I mean, eventually it's going to completely
No, well.
decay.
Oh, well.
Not
What do you mean?
Technically,
I mean, mathematically
That's a
it
half-life.
doesn't.
Yeah, but
Mathematically
you
it doesn't,
trade.
but you're saying, I mean, this is just a rough estimate, right? So another 50 years, how many particles will we have
I mean,
now?
you can't have half a particle.
Don't make it
Eventually,
Not 75. No, it's not 75. It's 70.
But we're not even at one
you
part.
can't like take a.
No,
Well,
it's
I
not
mean,
even
yeah, but
70.
eventually when you get there, you
No, wait,
can't
eventually it's not
split a particle
62.5.
and say
It's
you have
62.5.
0.325 of a particle.
Okay, so Aaron is right, but do you see how if we keep going in this kind of circle, let's just kind of circle where the particles are currently right now, right? Over a certain amount of time, okay, we're going to get to a point where it gets close to 1 or close to 0, but never actually hits 0. But we know in actual nature that there is a chance that it's all gone, okay, before we hit like however many half-lives it takes. So basically a half-life is this, the amount of time it takes for half of it to be gone every time.
Well,
Okay? Yeah.
Like, I thought, like, there's always going to be traces of it. We just can't find them yet.
You can look at it as that too. I mean, that's
I thought you
That's true, but there are instances where it completely dissipates and completely. What happens is it doesn't just decay into like the air; it turns into something else, a different element,
Yeah.
like a different compound. A
That's
good
what it
way,
means by it never disappears.
Yeah, trace of it.
I guess, in a way you can look at it is like rust. You guys know what rust really is?
Yeah.
Like it's like imagine you had a chunk of iron, and you have oxygen just floating in the air, right? Right, just like scheming little devils. Okay. So what they do is they latch on and like they create this piece where it's not really iron, it's not really oxygen, it's FeO2, I think. It's now rust, right? It's like as if the actual iron decayed, but what actually got off was not iron particles in the air. That'd be freaky, like, whoa. I just saw iron dust. It's weird, right?
So you're saying the iron actually did disappear, but it turned into something else.
That's exactly right. So decay, that's how decay actually
Yeah.
works, you know. So it might actually go in the air as whatever it is, but don't think it's just like floaty pieces of iron or something. Huh? You don't. Please don't bring chemistry back into your life. I'm sorry. Well, you're in my chemistry.
Yesterday.
Yes, it was. Stop it, Mr. Wake. Stop it. I'm having fun. I'm not having fun yesterday. I had fun today. Okay. All right. So that's the concept of a half-life. Did you have a question, Nathan?
No.
Oh, you're saying hi to Christine? Okay. So your formula for determining a half-life is going to sound a little odd. So here is, so I think we're on the third set. Were we? No, we did the fourth set last time, right? The third set of notes. Okay, so we're on the fourth set of notes for half-lives. And then in your book, you're going to have an odd general formula. And it's going to seem very arbitrary. General formula is going to be ln 2 over k, whatever your k is. That's your half-life. The thing is, we don't know where that comes from. Okay, I could show you where that comes from.
Sorry, what do you mean by an ln of 2? Is that like the natural log of 2, or is it the natural log of something?
You're right. It's just natural log of 2. And I like... Oh, okay, I thought Allie's face is like, I don't really understand what's going on. Like, this is kind of weird. What I want you to kind of realize, let's see. And this is equal to time, okay? So sorry. So t. Think of this as t, okay? T is equal to ln 2 over k, right? Okay, so what I'm going to try to do in the next 5 minutes, so make sure you're kind of ready to go on to the next class, is I'm going to show you where this is derived from, okay? And it's actually, this is derived from, ta-da, your general equation. Like I said in the beginning, that this equation, wait, why is it negative? Is it negative? Oh, it's going to be negative kt. I guess they're just trying to exemplify that it's the decay, and I think they really want to set that k to be like a negative value. Okay, even though k can be any constant, that's what's odd. Because I'm like, why would they need to specify? I guess they really want to bring it back in your head, like, hey, it's got to be a negative number. Okay, so your k has to be it will have to end up being negative.
Oh, because half-life you're taking something away.
And let's see here. What is it?
Is it always negative?
It's a half-life.
Oh, how come it was
We're always taking something away. We just said this.
Because earlier we were
Just
talking about
make it-
exponential. This is specifically about decay.
That's 1 over k, that's k to negative 1.
Because
It's exponentially decaying.
if it's growing like your money, you do not want a negative k.
Right.
Okay, you want your k to be, because then you end up with like this. I put $100 in. Okay, I put $100 in the beginning, and I put in 50 years of my life. I want to see what my money looks like. What is that negative number doing next to it? That's not good.
Oh no. Oh no.
Oh dear, am I losing money? It's like, yeah, you are. Sorry.
Vegas, is that you?
Okay, so you don't want a negative number. Just think of it that way. If it has to make sense in your head, you want a positive number. Okay, so this over here, what you're actually looking at when you're looking at a half-life is this is going to be your new value. Your initial value will be half of what it was. Does that make sense? So you know that if you started with 500 particles, right, over a half-time or a half-life, how much should you have after a half-life? Sorry, it's gone.
250.
250, right? What did you have to multiply to 500 to get to 250?
1 over 2.
What happened?
So what this is saying is in order to find a half-life, this has to equal this. That's where this equation comes from. So you would have to solve this problem, setting it equal to this. And then this is where you're going to get ln of 2 over k.
Natural log both sides, right?
Yes, so here's how you start. ln of 1/2, this will cancel out. You have negative kt, and you are solving for t technically, okay? It's equal to ln of 1/2, get over here, okay? And then you divide both sides by negative k. You get t is equal to ln 1/2 of k. I think I'm missing. Oh, I think because this is negative here. Sorry, there is one step that I am missing. This does go to. You will end up with what is it? ln 2 of k. I think it has. I forget the property here, but it has something to do there. Okay, so go back and really be mad
Is
at
this in the book too or no?
Mr. Lee. Okay, sorry. So, yes, this is in your book. Okay,
That's
so
fancy.
this is yeah. Yeah, if you look in your solutions manual, you will find this exact insignia here. Okay, all right, guys. I need to make a video with an example of this. Okay, but that's at least where this problem comes from. To solve for the half-life. So if you want to solve for why this keeps going to 250 and you want to solve for the time, the t. Okay, this is the equation you would use. Is that understood? Okay. Once you know your k, you plug that in. You just get the time. That's it. It's as simple as that. Okay. All right, guys. You guys have a great day. Okay.
Thank you.
No problem, guys.
Thank you, Mr.
No problem. Thank you for coming to class.
He comes every day.
Except for the days that he needs to be